All right, hey, what's up, guys? Happy Tuesday. Now we're visiting back to our toolkit for area and volume. Here we are on the second page here, areas of special shapes. Now, I know we filled in this for regular polygon. Make sure you have that. We'll be talking about that today because we want to talk about the area of a circle formula because look at this here, right? Area of a regular pentagon or the hexagon in this situation, regular polygon here, the formula is going to connect very closely to the area of a circle. And that is because any regular polygon, again, can be inscribed in a circle. So if we know all the kind of the machinery of how this works, this area of a regular polygon formula, in terms of its geometry, we can apply that to circles and boom, we'll get the circle formula for its area, which I know you guys all know, but let's see where it comes from, and I'll prove it to you very quickly. Before we can do the proof of that, though, let's talk about circumference, because circumference is another thing that comes up in your problem set today and also is an important thing to know about here. And you might be wondering, is this just kind of coming out of thin air, this formula that circumference equals 2 times pi, this mysterious mathematical constant, 3.14, what is it, 159265, times by radius length. Does it come out of nowhere, or is it just proven, right? Is it proven? Should we talk about a proof of this? Okay, so it's already up there. I have this formula, so make sure you have this down here on your toolkits as well. Write it in. C for circumference. I'm not going to write down what each letter stands for, but C for circumference. Okay, that's the big thing here. So it's uppercase. Other ones are lowercase here. So we got a lowercase pi symbol, 2 times by pi. No, not that pi. You don't eat it on March 14th. You throw it in teachers' faces, right? Pi day. But anyways, we have pi, right? Pi, Greek letter. And then R for the radius length here. And that's a calculation to determine the circumference, right? The length, which is different than the arc measure, right? Arc measure of a circle. Remember, a circle's arc itself has how many degrees in it? 360 degrees. So circumference is the length, right? The length of the darn thing. And what this is here, okay, circumference is a definition. Okay, so we don't actually have to talk about a proof of that for today, okay? Definition of circumference, okay, of circumference is technically this, okay, it's technically this. Circumference equals pi, there's a number pi, 3.14159265, times by its diameter, right? Times by the diameter of the circle. That would equal this circle's circumference, right? If we laid out this whole arc, right, which is the whole circle, if we laid it on out as a straight line, it would be 3.14 roughly, right? Well, it would be pi times larger than the diameter, right, than the diameter of the circle. So here we have an example of a circle whose diameter is 1. Well, then if our diameter is 1, what's the circumference? Well, it's just pi times that, right? It'd be 3.14. Keep going. It's an irrational number. You'll study pi more because pi is one of these fascinating and mysterious math numbers that come up in a lot of applications in math here. So, but where it comes from, the name pi is actually related to circles, as we're doing now here. So I actually wrote this down here real quick because we're going to use these formulas today, right? We're going to use specifically this one. Okay, we'll use this one in the circle areas proof in a second. But I just wanted to point out here that the number pi comes from a definition. Okay, it comes from definition. So down here is from Wikipedia, and because pi is so darn important in math, and because a lot of eyes are on pi, P-I, 3.14, yada, 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 you've all heard it a bunch of times before, but because it's so important, I can trust Wikipedia on this, right? I can trust Wikipedia on this because all the great mathematicians, right, have an eye. Wikipedia can't be wrong about pi, okay? Sometimes, like, Wikipedia is bad about certain articles that very few people look at, like if you have this article on this, like, random person or random celebrity or whatnot, Wikipedia might be just off, but pi, I'm sure tens of thousands of people go to the pi page on Wikipedia a day because they all love math as much as me. Anyways, here, the number pi is a mathematical constant, okay? What's a constant? A constant is a number that doesn't change. Pi is always 3.14159265, and it continues on with a bunch of decimals, and a lot of mathematicians have got things figured out to like tens of thousands of these decimals here, but do we know what pi is exactly? No, not quite. It's an irrational number. But anyways, the number pi is a mathematical constant. It is defined. Okay, so pi is actually defined. This is where this whole thing comes from, the circumference thing. It's defined as the ratio of a circle's circumference to its diameter, right? Ratio of circle's circumference to a diameter. So here, right? So if we have to do this here, circumference, okay, if we have to take the definition of pi real quick here, this is sort of going to show you where the definition of circumference, the circumference formula comes from, the ratio of a circle's circumference to its diameter would be c over d, and that would equal pi, okay? Ratio of circumference to diameter equals pi. Well, how do we get to these formulas for circumference? What did I do? Well, I just cross multiplied here. Pi times d would equal c times y1, or c equals pi d. Okay, pi d. So if you got the diameter, just multiply by pi, gets you a circumference here. It comes from the definition, okay? And this is a definition because this is something that people have noticed, right? Have noticed for millennia. Here we are. We're on Wikipedia right now. Check it out here. People just noticed this. Check it out here. Look at this pretty sweet graphic right here. I take a circle with a diameter of 1, roll it on out, right? Roll out, do one revolution, right? One revolution, one turn around that whole circle. It's gonna be, this whole length is 3.14159, and it goes on the decimal times longer, okay, as I laid out here. So check it out here. That's the length pi, okay? If this is, if a real postulate tells us that that's a diameter of 1, then its circumference is 3.14, about 3.14 times longer than that here, okay? And it comes from what we've noticed. And then we said human beings have just been like, well, let's give that a definition. Let's define, let's call this, whatever this ratio is, we're gonna call it pi, okay? So this all comes from a definition here about what human beings have noticed. And I'm hoping in middle school you've played around with this and noticed this, that the circumference of a circle is about 3.14 times larger than its diameter, okay? Where did the other one come from? Well, obviously we've studied that d equals 2 times by pi, 2 times by r. Diameter is twice as long as its radius. So if we do substitution into this one right here, we get c equals pi times by 2r, or just 2 pi r. And that's typically how the formula is presented to students, because the radius is actually a more significant length for a circle than the diameter, right? Because remember, a circle is the set of all points in a plane that are each equidistant from a fixed point, it being the radius. So anyways, this is the way we usually see the formula. All right, second thing up here, hopefully I haven't bored you to death with that. Hopefully I found that somewhat interesting here. I want to get to this. I want to actually prove this, okay? Because this is a theorem. This is the theorem that I can prove for you right now, okay? Proof of this, of the circle area for, it's a theorem, and I'll build upon the last video I made for you, which had you fill in the your toolkits here, your area and volume toolkits here, was for the regular polygon. We got to this formula here, okay? These are ridiculously related, and hopefully you noticed that in Monday's class, okay? And you can kind of get through it, but I'll try to get through it really quickly for you guys right now. Area of a regular polygon is going to connect us to the circle here. So let's pay attention to it for a second, and then eventually I'm going to prove it right here. It's not going to take much space here about what the area of a circle is. And you guys know the formula here. But I want to show you where the formula comes from, okay? Circumference came from definition. Circle area, we're going to get to the theorem in a second about what the formula is here. Regular polygon equals 1/2 the apothem, not pronounced apothem, it's apothem, believe it or not, times by the perimeter of the regular polygon here. Okay, so just reminders on language. We have the apothem as a new thing. So remember, this is what we're hoping to get you guys out of regular polygons, is that regular polygons can be broken up into triangles. Okay, it can be broken up into triangles. So here we have the radius. This is actually be the radius, right, of the circle down here. So notice here I have the circle in purple. I got the regular polygon in purple up here. We have a radius here, but the radius isn't that significant to finding us the area of the regular polygon, because it's like a side of one of these triangles. Remember, as many number of sides you have in a regular polygon, that's how many triangles you're going to have formed with this central angle right here of the regular polygon. The way to get the area, remember, is we got to take not the radius of the regular polygon, or of its circumscribed circle, we got to take this right here. Okay, we got to take it the apothem, which is the altitude from the center of the regular polygon to any of the sides. Okay, so I got an apothem there, 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 I got a whole bunch of apothems. Okay, but what do we notice about the apothem compared to the radius, for instance, here? Okay, the apothem is shorter, it's smaller. Okay, it's smaller than the radius is, and that's going to be important when we get down to this here, when we talk about, well, where's the apothem on a circle? What can we describe as that? Okay, so anyways, remember this one here, we got the apothem, and then, right, we got to multiply the apothem by this side and divide by 2 to get the area of this triangle. We got to multiply the apothem by that side, divide by 2, and get the area of this triangle. So remember, the area of a triangle is 1/2 base times height. Base times by apothem, divide by 2. side length times by apothegm divided by 2, base of this triangle times by apothegm divided by 2, and finally this one here. So suddenly we've gone around the whole perimeter, and we've multiplied the apothegm, we've divided by 2, reminder. So that's why the formula works out that way, okay? Because the apothegm is the height of all those triangles, and the perimeter is the sum of all the bases of all those triangles. And then we always have to divide by 2 for any areas of triangles. So that's where the formula for the area of regular polygons comes from. Here's how it comes into play with proving the area of a circle formula, which you all know is pi r squared. At least I hope you do, okay? Remember, circumference, 2 pi r. Doesn't have a squaring in it. There's no exponent right here. There's no exponent right here. This is going to be pi r squared. Where does it come from? Well, what I'm actually going to do to prove this is I'm going to put in the area of a regular polygon formula up top here. I'm just going to put this in. I'm going to pretend this circle is a regular polygon. And then we'll think about what the perimeter is for a circle and what the apothegm would be for a circle, okay? So check it out here, right? I got this right here. I got the circle center in the same place as this regular polygon right here. If I had to draw, and if I'm just using this formula, let's see, I'll extend this formula to circles, okay? Sometimes you can make assumptions like this. If I kept adding sides to this hexagon and then it became an octagon, then it became a decagon, then it became a hectagon, and then it got bigger and bigger and bigger. It became a 200-gon, it became a 1,000-gon. Eventually, it's going to look like what? It's going to look like a circle. So we should be able to use this formula, right? Because, when we have 10 million sides that are all the same size and all the angles are the same, right? Basically 100, almost 180-degree angles, they're interior angles here. It's going to be a freaking circle, but we could still use this formula because this formula is proven for us here. So the question becomes, what is the apothegm of the circle? Okay, the circle, not of the regular polygon here, because it's not A, right? I could call this the apothegm of the circle because it's just the same thing as that we have up here, and this is perpendicular to the side, so I'm just going to the circle itself. What did I draw there? Well, I draw a freaking radius. That's pretty obvious here. So instead of having A be in our formula for the area of a circle, I can put in R, right? I can totally put in R, okay? And then I think you probably see what I got to do next. Instead of putting in P, right, for the circle, what's the word we have for the length? Not the sum of the lengths of all the sides of this circle, because the circle, again, doesn't have sides. What does it have? Okay, well, it has one continuous arc here. It's all these points here. What if we laid them all out? What do we call that? Well, we can put in circumference right there here, okay? But we can be a little more specific like this because what do we know circumference to be defined as? Okay, circumference equals 2 pi r. Okay, equals 2 pi r. So check this one out. Let's go ahead and wrap this thing up. Let's finish this proof. Well, I'm just trying to prove the area of formula for a circle. I'm using, right, step one, I would state the area of a regular polygon formula as my justification. Area equals 1/2 a times by p. Then I would say that the apothegm of a circle would be equal to the radius, right? Equal to the radius here. So I would, by replacement, by substitution, I would replace a with r. And I would also say that the perimeter of a circle is, for circles, the perimeters of circles is the same thing as circumference. So I would take the circumference formula, 2 pi r equals the circumference of the circle. I'll replace that into the formula. And what do we notice? We can simplify this now here too. 1/2 times by 2 would equal 1. So those would cancel each other out. And now I can multiply my like variables here. R times by r equals what? R squared. Pi times by, don't have other pi's there, just equals pi. So area equals pi r squared. And that, my friends, is the formula for the area of a circle. Area equals pi r squared. And so you have it proven now for you. You have it in your toolkits, I hope. And hopefully you found this talk at least somewhat interesting in that these formulas do actually come from somewhere. And I think that's pretty neat that we can build upon our knowledge and get it out there and know that everything kind of connects here together. Thank you guys so much for watching. Remember, area formula for a circle here, that's the one with the squaring in it. That's the one with the squaring in it. So remember, what's the area of a square? S squared. What's the area of a circle? Pi r squared. Okay, so squaring because it's area. The one that circumference is 2 pi r. The 2 isn't the squaring. The 2 is in front. Okay, so I just say that because a lot of people confuse those formulas. Area of a circle formula, they might say 2 pi r. No. If it's area for a circle, choose the exponent. Okay, hopefully you kind of get that. We got to do r times by r in the proof of it. Okay, hopefully that helps you. Thanks for watching. I think I have another video going through the some of the problems that are on today's problem set. So hopefully I'll help you out. But hopefully you get challenged by these questions. Take care. Bye.